Hello and welcome back to the course. So today we're looking at second order linear ODEs, so starting on second order or higher than one, which is what we've been doing basically till now. We're starting chapter 2 in the book, so section 2.1. And you can get the book at this link. It's also in the description. You can browse the book as a PDF or as web pages, or you can get a cheap paperback if you want. All right. So what are we looking at? We're looking at second order linear differential equation. So something of this form where y is the unknown and a, b, c, and f are some functions of x. Now, if a is ever zero, we get into trouble. So a lot of times we're looking at equations like this. So we basically divide by a. So we divide by a, we get something like this. So you have y double prime plus other stuff, right? So we'll call it pq and little f. Now linear, if you remember, means that there's the only way that y prime, or y double prime, because it's a second order equation, appear is linearly. They never appear as powers, and they never appear as, there's no functions of, there's not like e to the y or something, right? So we, there's only first powers here. Maybe something that doesn't depend on y at all. That's the right-hand side, but, that's what linear means, right? Homogeneous means that this f is zero, right? So really, every term then depends on y, but linearly, right? So that's what we mean by homogeneous. Homogeneous are a bit easier to handle. All right. So some examples, and we've seen some examples at the very beginning. So for example, this guy y double prime plus k squared y is 0, where k is some constant. This has the solution cosine kx and sine kx. And if I put a minus sign over there, I actually get the e to the kx and e to the minus kx, right? So we found these guys, and you actually have multiple solutions here, right? Now this is where your superposition comes in, right? So suppose that we have this homogeneous second order linear ODE, and suppose that we found two solutions, y1 and y2, just like we did just a moment ago. Then if I take this so-called linear combination, so basically if I take two constants, c1 and c2, and I take c1 times the first solution plus c2 times the second solution, that function is also a solution, right? The solution to this equation, right? So I can, once I have two solutions, I can construct more solutions by taking these linear combinations. Right, so that's just the definition of this word. All right, so let's prove this, because it's here. We're generally not proving things, but here the proof is actually relatively simple, and actually it's a good way to see what how do linear equations work, right? So suppose that we have these y1 and y2 are these solutions, and we write y, this new function that we hope is a solution, as this linear combination. And let's see if it satisfies the equation, right? So we plug that in, right? So we take our y and we plug it into the left-hand side, and we're trying to see if it's 0, right? So that's just because y is this linear combination, I just put in that linear combination here, right? And now, well, you take this second derivative, so you You can remember C1 and C2 are constants, right? So for example, when I'm taking a second derivative here, it's really C1 times the second derivative of y1 plus C2 times the second derivative of y2, right? And so we do that everywhere here. And then we can group things together, right? These guys all have a C1 in there, right? So we could group it together. Those guys are giving me this term, and then these guys give me the second term over here. And now I notice something. This and this are basically, those are the sort of left-hand sides of this equation with y1 and y2 plugged in. But those are solutions, right? These things, y1 and y2 are precisely the sort of functions that give me 0 when I plug them into the left-hand side here, right? So what we got here really is C1 times 0 plus C2 times 0. That's just 0, right? So that means that this really is 0. Okay, so this is just a small computation, and we see that this superposition works, right? Basically, we superimpose two solutions, on top of each other, and that's again a solution. As long as we're talking about homogeneous second-order linear equation, well, any linear equation, homogeneous linear equation will work. All right, so let's see this in a slightly more general but nicer to write way. So an operator is sort of like a function, but it's a function that instead of eating numbers, it eats functions and spits out functions, right? So a function generally is something that eats a number and spits out a number, but it could be a function of something else. So an operator, we usually mean it's something that's going to eat functions and it's going to give me back functions, right? And in particular, we're going to have a so-called linear operator. So let's define the operator. Let's just call it L. Why not? And let's define it as L of y. So it's supposed to eat y, and it will give me this function, right? Which is the left-hand side of that equation that I was looking at. So once I've made this definition, this is what Ly is. The homogeneous differential equation becomes Ly is 0, right? It's it's basically telling me that it's the set of functions that L kills. That said, those functions are solutions to these equations. All right, so the operator is linear. If this is true. Now, if you've had linear algebra, this is basically, what how you would say that a matrix is a linear function, right? Is linear on, you're plugging in vectors and getting vectors, and being linear is precisely this sort of relation, right? It's that I can if I have a linear combination inside, I can take it out, right? And it's basically almost like if we're multiplying by L, right? If L was something that I could multiply by, it's not really a multiplication, but it almost acts like that, right? So that's the way that you want to think of it sort of formally. And now there's a really nice short proof of the theorem if we use this operator notation, right? And this, right? So suppose that we have two solutions. That means that L of y1 is 0 and L of y2 is 0. So y is this linear combination, right? That's this, right? So if I take L of y, well, it's just what it is, right? Now we have this, it's a linear operator, right? So I have that it's equal to this, right? C1 L of y1 plus C2 L of y2. Well, but these guys are solutions, right? So therefore, I get 0. So I get a solution, right? So that's the way this works, right? And it's, again, if you've had linear algebra, This is basically the proof of y is the kernel of a matrix. Y is a subspace. I can take any two things, any two vectors that a matrix takes to 0. I can take any linear combination of them, and that the matrix still takes it to 0. It's basically the same exact proof, right? And that's because it's just this linearity. It's a linear operator. So it's just acting on functions instead of vectors. All right. So let's look at an example of a well, one that we've seen already. But let's see this in practice, right? So if we have y double prime minus k squared y equals 0, so we've seen before that we have these two solutions, right? Somehow we check them, we figure out these are solutions. These work. Now we can write these new functions, these hyperbolic sine and cosine, in terms of exponential, in terms of e to the t and e to the minus t. Now that looks a lot like what I have here, right? So if you, instead of t, if you plug in kx, so let's look at the cosine, cosh, right? Hyperbolic cosine. And let's plug in for t, let's plug in kx. Well, so I have, well, I'm basically just plugging into this formula, about is kx. So now, if I do just a little bit of algebra, I have a constant times e to the kx plus a constant times e to the minus kx. All right, well, this is y1, and this is y2, right? So I have a solution. So cosh is also a solution, right? Sinh, again, is a solution for the same reason, right? So now there's just a minus sign, right? And so everything works the same. I'm just have minus a half in here, and therefore this is a solution, right? So we started with two solutions, and we wrote two more solutions, right? Or two more different versions of of the solutions. It'll turn out that for a second order we only need two solutions, but so we have two different ways of writing solutions to this equation, and that's just using superposition. All right, now here's an exercise just in case you haven't seen cosh and sinh. They act very similarly to cosine and sine. They don't look similarly. They don't oscillate. Cosh is really, it's not a parabola, but it's sort of looks kind of like a parabola, and sinh is sort of, well, not quite a third power, but kind of has that shape. And you have, well, these guys, those are familiar, right? Cosh at 0 is 1, and sinh at 0 is 0. That's good, but you don't get them. You don't get these at other points. This is not an oscillating, not a periodic function, right? But at 0, you have the same sort of values, and derivative of 1 is the other, and now it's actually even nicer than with sine and cosine. So derivative of cosine is of hyperbolic cosine is just the hyperbolic sine, and derivative of hyperbolic sine is just hyperbolic cosine. So I don't have to worry about the minus 1, right? Now they also satisfy, just like sine and cosine satisfy the fact that they're basically parametrizing a circle, right? So you would have a cosine squared plus sine squared equals 1, right? Because x squared plus y squared equals 1 is the equation for a circle. So here it's really well, I have this minus sign, so x squared minus y squared equals 1. That's an equation for a hyperbola. That's why they're called hyperbolic sine and cosine. All right. Now, let's look at existence and uniqueness of solutions for second order linear ODEs. So suppose that I have P, Q, and F are some continuous functions defined on some interval. Let's call it I. Let's suppose A is a number, some number in I. So, could be on the endpoints. It could be somewhere in the middle. And let's suppose that B0 and B1 are just any numbers whatsoever. They're just constants, right? Then the equation, this second order linear equation, here not necessarily homogeneous, it has exactly one solution. So it has a solution, and there's exactly one that satisfies these initial conditions. Now, this is slightly different than before. For first order, we had only this guy. So now to get the uniqueness, we need to actually give a little bit more information, right? And that's really because we have, just like for the like y double prime minus y equals 0, we get the exponential and the e to the x and e to the minus x, right? We get two sort of very different solutions. We're really going to have two very different, two different constants in there that we need to solve for. So you really need to give two initial conditions. So a natural thing to give is to give the value of the solution at one point. So we're doing it at this point A. And also, we need to give another piece of information, so we'll give the derivative, right? So it's the value and the rate of change at one point. Once you specify the value and the rate of change, then you have then the solution is unique. It's at first it exists. I know that I can specify this and I can always find a solution, but also it's the only solution, right? And again, this is good, if you're doing some physics, or if you some engineering, or you have some sort of a problem, and you model it with a differential equation. Well, you certainly hope that if you haven't done any mistakes, that there's a unique solution, right? I mean, if you throw a ball and then all the parameters, the ball should land at a precise place that you could compute, and there shouldn't be sort of different solutions, and just depending on how the universe is feeling that day, the ball will land either here or there, right? If you know all the information, there should be a unique solution, right? So that's basically what this is saying. So here, if I know the equation, and I know the initial position and velocity, basically, then I know the solution, well, at least wherever the equation is defined. All right. So let's see an example with so here it's sine and cosine. So suppose I have this y double prime plus k squared y, right? And let's make a be 0, because that's a convenient one. Here I would just be the entire real line. And let's suppose that these can be any constant whatsoever, b0 and b1, just any number whatsoever. Then I actually have the solution to this equation with these initial conditions. I can just write it down. Now let's double check it. Let's verify the initial condition, right? So let's just plug in 0. So cosine at 0, and then sine at 0 over here. So cosine is 1, sine is 0. So I just get this number. I just get b0. Well, okay. So that's this initial condition. right? Now to specify it, to check the other one, we need to take the derivative. So we take the derivative. So that's going to be this, right? We're taking a derivative of this expression over here. So we're going to have, so over here I have a k coming out. Also the cosine changes to a sine. Oh, there's a minus sign, but who cares about that? It's not going to be that important. And over here, the sine changes to a cosine, and the k comes out, so I just get b1, right? Now, if I plug in 0, well, this sine, what used to be a cosine before, now a sine, so now when I plug in 0, the first term just disappears, right? Because sine of 0 is 0, right? So this thing just goes away. And on the second term, cosine of 0 is 1, right? So I just get b1, right? I needed to have, in this formula, I needed to have k here because that's going to come out when I'm differentiating, right? So that gives me b1, right? Now, you can also do the same thing with, if you have the minus sign. If you use cosh and sinh, it's exactly the same idea. So the only thing that's going to be different in this computation is that well, there's going to be there will be h's here, right? So sinh and cosh instead of sine and cos, and this minus sign is not going to be there, right? But other than that, it's the computation is going to be exactly the same. So that's going to give me these initial conditions b0 and b1. All right. Now, so what we've just done was we were able to solve for the initial condition because we had two different solutions. Now, what did we mean by different, right? Because, for example, if we had before, if we have sine of kx and 2 times the sine of kx, I mean, in some sense, those are different solutions. But taking linear combinations of those will not give me anything new. They will just give me different multiples of sine, and that's not going to give me every possible solution. For example, there's no way to write cosine as a constant multiple of sine, right? And that's really what we want. We want the solution should be different. So we're going to call them linearly independent. If one is not a constant multiple of the other, right? That's really what we want, right? So, so if we have two solutions and one is not a constant multiple of the other, and we have a homogeneous linear ODE, second order linear ODE, then we actually have the general solution. The general solution is an arbitrary linear combination of the two given solutions, right? So here are my two constants, arbitrary constants, right, in the general solutions. Right, so what we really need to find if we're solving a second order, linear homogeneous ODE, what we need to find are two linearly independent solutions, and once we have that, we've got a general solution, right? We just write down this linear combination, and once we have a general solution, we can solve for any initial condition, right? We're going to give the initial position and the initial velocity, right? So the rate of change, right, at some point, right? So the value at some point and the derivative at some point, and you're going to get two equations for C1 and C2, and you can solve them. And once you figure out what C1 and C2, you have your specific solution, right? You have the solution that you're looking for. All right. So let's see an example of it. So for example, let's just set k equal to 1, right? So I have sine and cosine are solutions to y double prime plus y equals 0. Now, why are sine and cosine linearly independent? They're not constant multiples of each other, but how do we see that? How do we, I mean, they don't look like it, but why is it true? So let's argue this. So if sine is a constant multiple of cosine. So if sine of x is a times cosine of x, you can write it in the opposite order. That's fine. That's, there's no, you don't have to say sine of x is a times cosine of x. You could do the other one. But let's write it like this. Sine of x is a cosine of x, right? For some constant a. Well, and there's a couple of ways that you can argue this. But first, well, I could plug in x equals 0. If I plug in x equals 0, I get sine of 0, which is 0, is equal to a times cosine of 0, which is 1. So I just get that a is 0. Whatever constant is, this is supposed to be true for all x, right? So I could let x be something, let's say 0. And that tells me that the a must be 0. But then, if a would be 0, then sine of x would be 0 for all x, right? If this is supposed to work for all x, right? But it's nonsense. I know that sine of x is not 0 for all x, right? Just take, let's say, pi over 2 or something, right? Sine of x is not 0 there, it's 1, right? So that means that no such constant existed, right? There are other ways of doing this. Like, for example, you could just divide the two, right? So you could divide by cosine. You'd get tangent, and tangent is not it's not constant, right? So there are various ways that you can argue this. The easiest usually is to sort of plug in a couple of different x's and get some sort of some sort of a nonsense, some sort of contradiction coming out of it, right? So that's the way that you check if two things are linearly independent. You just suppose they were linearly dependent. Suppose one was a constant multiple of the other, and you just play around with that and see that that's nonsense, right? And we're gonna see that over and over. All right. Now, that means that y1 and y2, which are sine and cosine, are linearly independent, and therefore this is the general solution to this equation, right? So that's what this term says, right? You just have to, well, once you have enough solutions, once you have two solutions here, as long as they're linearly independent, you're done with the general solution, right? You found the general solution because it's just a linear combination, an arbitrary linear combination of the two solutions, right? So really what the way that we're going to try to solve these kind of equations is by trying to find, well, if they're second order, by trying to find two equations and hopefully find two equations which are linearly independent. Once we do that, we're done, right? Okay. So another example. So this equation over here, y double prime minus 2 x to the minus second power, which is 1 over x squared, right, times y is 0. Now, you can double check that this has solutions x squared and 1 over x, right? Hopefully I've done that correctly, right? And let's not worry about how we figure that out, right? But let's just suppose somehow you know that that's true, right? You can plug in to check, right? If I plug in x squared, the second derivative of x squared is 2, right? So this would be 2. X squared times x to the minus 2 is just 1, right? So minus 2 times 1, so it's 2 minus 2. That does equal 0, right? So x squared is a solution, and you can do that for 1 over x. All right. So now let's see that they're linearly independent. Well, suppose that they were linearly dependent. That's essentially the way it always starts, right? So suppose y1 is a constant times y2. So let's solve for a. I mean, that's one way to do it. We solve for a. That's y1 over y2. Y1 is x squared. Y2 is 1 over x. So y1 over y2 is, well, 1 over y2 is x, right? So we really have x cubed. Now that is not a constant, right? So yeah, so a couldn't have been a constant, right? So that's just like before when I said divide by cosine, you would get tangent. So however you want to show that a can't be a constant, right? You do that, right? So these really are linearly independent. Now, should warn you, it's not always totally trivial to see that something is linearly independent, because you might have things that look different. They have different formulas, but they might still be, constant multiples of each other, right? So it's not always totally immediate. For the other thing is this is for two functions, and we're going to see later on with more functions once we have a higher order ODE, and then it gets even more complicated. So for two functions, it's often fairly easy to check that two functions are not linearly independent, or that they are linearly independent. That's really what you want. But for more, it's going to be a little bit more complicated. But even for two functions, it's not, you can't always just look at it and immediately see it. It's sometimes obvious why. Sometimes you have to do a little bit of work, right? Okay. So so we have y1 and y2 are linearly independent. Therefore, also that I just said that, right? Forgot to move the slides. Therefore, this is where I wanted it to be. This is the general solution, right? So suppose that we somehow figure out one solution, either by guessing, because for some equations it's fairly easy to guess one solution. There might be one really simple solution that you can just get by just looking at the equation and say, oh, this might be a solution. But how do I find a second one then? Because I need two, right? Might be one easy one and one really hard one, right? So somehow I figured out one solution. How can I find the other one, right? So this is the sort of reduction of order method. So there's actually a procedure that you can follow to find a second one. So suppose that I have one solution, y1, and it solves this equation, this second order homogeneous linear ODE, right? So we try to find a second one, y2, and it's going to be y1 times v. So it's going to be a multiple of y1, but not a constant multiple. It's going to be, this v is a function, right? So this v is not going to be a constant. It's going to vary as x varies, right? So hopefully that's going to give us a different, a linearly independent solution. So obviously I could take just a constant times y1, but again, that doesn't give me, anything new. All right, so let's plug that in. Let's plug y1 times v into the equation. So that's y2, right? Is y1 times v, right? So let's see when, what condition on v is this going to force, right? I really am looking for a v. I know y1 already. So if I find a v that makes this y2 be a solution, I'm done, right? So I plug that in, and I'm not putting in the here this of x and of x, because then that would be too many of x something, right? So over here is y2 double prime. That's just applying product rule, and you have to take two derivatives. So what you get is this expression over here. That's y double prime, y2 double prime, right? If y2 is y1 times v, then this is y2 prime. This is one derivative, so one product rule, and then y2, y1 times v, I'm not taking any derivatives. That's just what y2 is. All right. Now, if we rearrange this a little bit, so I group all the terms which have a v double prime, v prime, and a v, and I group all those together because all of them are multiplied by v, v prime, or v double prime, right? So there's only one guy with a v double prime. That's this guy, right? There is v prime. There's going to be one here, so it's going to be p of x times y1 v prime, and there's also this guy over here, right? So that's what I'm getting over here. 2 y1 prime plus p of x times y1, right? That's getting me this term. And then all the other terms are just multiplied by v, right? So you have y1 double prime. Then I have p of x times y1 prime. And then I have q of x times y1, right? That's over here. And what I notice is that this is precisely the left-hand side of the equation, right? And y1 is a solution. So this thing is just 0, right? This just goes to 0. So what we're left with is we want everything over here to be 0, right? We know that this is 0. So that means that this had better be 0. So I get this equation out here. Okay, you say, well, it's again a second order equation in v, but now notice that there is no v. There's only v double prime and v prime. So if we just change notation a little bit, I'm going to call v prime w, because then there's just w and w prime. So then I get this equation. That's a first order differential equation, right? It's a first order linear differential equation. We have a formula for that, right? It's we have the integrating factor method. I can just plug this into the formula and get get w, right? So we solve this for w. We have a formula for that. We know exactly how to do that. We don't have to do any more guessing or anything. So you find w. Now w is not the thing that I'm looking for. I'm looking for v. So I get v by anti-differentiating because w is the derivative of v. So to get v, I anti-differentiate. Now, of course, v is also not necessarily what I'm interested in. I'm looking for y1 times v, but I just multiply y1 and v together, and I get y2. All right, so let's look at this in practice. So you might notice that y1 equals x solves this equation over here. Y double prime plus 1 over x times y prime minus x to the minus second power times y equals 0, right? Let's just check that that's that would work. So if y1 is x double prime is 0. It's not there, right? This thing just goes away. Y prime is 1, right? So this bit is 1 over x, right? Minus x to the minus 2 times y1 is x, right? It's x. It's just 1 over x, right? So this thing is minus 1 over x. 1 over x minus 1 over x is 0. Okay, so we have a solution. We might have guessed this, right? Because, you might have said, well, let's see if something like that is true, right? I mean, you might sort of, anyway, however we got it, we somehow got it. We figured out that x is a solution, and we want to figure out the second solution, right? So let's write down this this equation over here. So y1 times w prime, so it's x w prime, right? Plus, and now I have this this thing out here, right? Claim that it's 3. Let's double check that it really is 3. So y1 prime, that's just 1, so it's 2, right? I'm just getting 2. And over here, p, what is p? P is this guy over here, so it's 1 over x. Y1 is x, so 1 over x times x is 1, right? So this is 1, right? So I get 2 plus 1, I get 3, right? So I get x times w prime plus 3w is equal to 0. So I solve this equation, right? That's just the first order, a linear ODE. You solve integrating factor method, however you want to do it, and so you get this solution over here. So that's the general solution to this guy, right? I anti-differentiate because I want v, right? So v has this form, right? So it's just this is really c over x cubed, right? So anti-differentiate, I get this guy over here. Now y2 is well, now I have v. I multiply by y1, and so that gives me the second solution, right? So well, so if y1 was x, so if I multiply, I get, well, this x squared, becomes x, right? So that's what I get. That was the second solution that I got, and I even have this arbitrary constant in there. It doesn't really matter what arbitrary, like I don't want to take 0 because that would just give me 0, but otherwise any c will work. So I can actually simplify this a little bit. If I let c be minus 2, then I'm just gonna get 1 over x here, right? So why don't we just do that, right? I'm just looking for one solution, right? One solution that's linearly independent with x. So I don't have to, take all of these different c's. I'm going to be multiplying it by an arbitrary constant anyway in the end, right? So I get 1 over x. So the general solution, and you can check that 1 over x and x are linearly independent. And the general solution is then going to be this, right? It's going to be a constant times x plus a constant times 1 over x, right? That's the general solution to this equation. And basically it started by, well, as long as I could find one solution, I could find the other. Now, you can even write down explicitly a formula, but it's not always useful to just plug it into that formula, right? But if you work out, you take the w, right? The equation for w, you write down the formula for the integrating factor method, and then you also integrate that. You get this this expression over here, right? So you could plug into there, right? But I wouldn't be able to memorize that. I'm not that smart to memorize that. If you just remember that you're looking for a solution of the form y1 times v, right? Which is fairly easy to remember. Then you can just work this out, right? It's just, well, what do I need to be true? I want it to be a solution. That's what we're doing here, right? And it's much easier to remember that something like this worked than to work through it than to memorize an equation like this, right? All right, now for next time, a useful warm-up exercise is to try to solve this equation, right? And just find two solutions, find two distinct solutions, and they should be linearly independent. And then write down the general solution. Now, the hint is to try a power of x. So x to the r, right? Where r is the unknown. So try to look for what r should be, right? And equations like this are actually called Euler's equations or Cauchy-Euler equations, right? So they're in general they would be some constant times x squared y double prime plus some constant times x times y prime plus some constant times y, right? So all right, so that's good for now. So next time we're going to look at constant coefficient equations, and there we have a nice procedure for solving. It's somewhat similar to this, and those come up sort of more often. So we're going to look at those and how to solve them next time. So, all right. So see you then.